Hello dear students, here we are going to learn our topic, that is CHI-230 inorganic chemistry. We are going to learn the second section of the inorganic chemistry, that is bioinorganic chemistry. We already discussed the metallobiomolecules and the proteins which are used for transportation and the storage. We learn the electron carrier proteins, and next, that is the oxygen carrier and the storage protein. Last lecture we learned about the structure of myoglobin and the hemoglobin. Okay, today we are going to start the next topic related to the hemoglobin and the myoglobin. Here, this is the structure of oxyhemoglobin and the oxymyoglobin. Here, whenever what happen, whenever this is the deoxy form of the myoglobin, and which is similar to that of the oxyhemoglobin. Here, the deoxymyoglobin, which has a proximal histidine, at this stage this Fe has +2 oxidation state, and that time these Fe2 plus, which is having high spin, that time they have the number of electrons. The Fe2 plus system has the D6 system is there. Okay, and that time here their energy level are like this Fe, which has 2 energy level, and at this T2G level, this is called as a T2G, and this one is called as a EG level. In case of T2G, here there are the 4 electron and they shows the high spin. Why? Because this histidine and its porphyrin ring is the weak ligands, and that's why they shows the high spin structure. That's why here the 4 electron which is present into the T2G orbital, and here there are the 2 electron which is present in the the EG orbital, and that time here they has the maximum radius, that is what, 92 picometer, and here there are the unpaired electron are present. That's why this structure is the paramagnetic in nature. Similar things will happen in case of the oxyhemoglobin also. Okay, here this can be happen in myoglobin and also hemoglobin. Okay, here then what happened here, whenever these ligands or this histidine which is attached to the Fe, this Fe which is present to the above the plane of the porphyrin ring, that time what happened, this Fe which is present outside the porphyrin plane, above the plane. Okay, and whenever here what happened there, then whenever oxygen is going to bind to the Fe, then it push this oxygen, which pull or this push this Fe, and it is goes to the inside the porphyrin plane. How this happen? Because this oxygen, which is a strong ligand, this is a strong ligand, and that's why here this Fe get converted to the Fe3 plus state. That time they shows the low spin. Why? Because oxygen is a strong ligand. This is a strong ligand, and that's why they shows the low spin, and that here this radius of this Fe is going to decreased, and that's why here they shows the diamagnetic in nature. Okay, what is the role of distal histidine? Here this distal histidine play or with this bend this Fe structure like this manner. This bend this Fe structure like this manner, and that's why here this make the oxygen to bind in a bend fashion. Okay, this distal histidine which provide a oxygen to bend to bind in a bend fashion, and that's why they make it difficult for the carbon monoxide to bind in a linear fashion. Why? Because here this carbon monoxide which has the capacity to bind the Fe, but this CO which can be bind Fe in a linear fashion, and here this histidine which first of all this is in deoxy form, this is proximal state, and here then whenever in a oxymyoglobin manner it get converted to the distal histidine, and this distal histidine which bind the oxygen in the bend fashion. Okay, he force the oxygen to bend, and then this bended oxygen is bind to the Fe. Okay, that's why here this distal histidine is very important. Here why we are not going to bind the CO, because there is isolated heme which can be binds the CO 25,000 times as strong as the oxygen solution. Okay, that's why here in a living system binding affinity of the oxygen is reduced considerably. The for CO to bind strongly, it has to bind linearly, which is made difficult by the distal histidine. What happened here? Whenever this Fe which is goes to the binding position to the oxygen in that solution, the CO is also there. Okay, but CO has a ability to bind Fe in a linear manner. Okay, and then here whenever the CO is bind to the Fe, then this hemoglobin shows a poisonous effect which cannot be bind the oxygen. Okay, and that's why here this histidine which provide the Fe, histidine get converted to the distal form and it provide the Fe to bind the oxygen in a bended manner. Okay, and that's why here this is very important. Here this is the deoxymyoglobin proximal state, and here this is the oxymyoglobin which is in a what oxygen is bind to this state. Okay, the basis of oxygenation remain as same for the hemoglobin and the myoglobin. That means the mechanism of binding of the hemoglobin and the myoglobin are the same, but what is the difference of that? Only one difference is there. Here there are the 4 units of hemoglobin which is same time bind to the 4 oxygen molecule, and in case of myoglobin only one myoglobin which is bind to the only one oxygen molecule. Okay, here the begins what happened. First of all, this histidine, proximal histidine, which pulls the Fe to get inside the porphyrin ring and which bind the oxygen properly. Okay, what is the function of that? Here this histidine which pulls the Fe, here this at the first time this is in a proximal state. Proximal state means what happened here? This Fe which is present above the plane, this present above the plane of ring, porphyrin ring, outside the porphyrin ring. Okay, and then what happened? This histidine goes to the distal manner. That means what happened? This histidine which pull the Fe and inside the porphyrin ring. Okay, and that's why here they shows a planar structure. They shows a planar structure, and that due to their planar structure, this oxygen which bind in a bended shape to that of the Fe, and that's why CO cannot be bind to the Fe molecule. Okay, this is the mechanism of the binding of the oxygen. Let me see here the prosthetic unit part of the metalloprotein perform its normal function without the protein unit around it. If the protein unit is not around it, then what happens? This is a free heme group which is reacted with the oxygen. This oxygen which is banded like this manner in a bent shape. Then this bended shape Fe2 plus which is reacted with the another free heme, then it get converted to the 2Fe having 4 plus oxidation state. Then this 4 plus oxidation stated Fe containing oxygen which is banded to the Fe2 plus, and then this Fe4 plus get converted to the Fe3 plus which is banded to the oxygen. The reversible binding of oxygen is also possible on when the protein unit is present around the heme unit. Okay, this is about the mechanism of the hemoglobin and the myoglobin, both having the same mechanism of the binding of the oxygen to the hemoglobin group. Okay, here this mainly the hemoglobin which is divided into a two state. Here the hemoglobin which is divided into two state. First state is called as the T state and second one that is called as the R state. This is also very important and asked in your examination. T stands for tense and here R stands for relaxed. R stands for relaxed. What it means here? T, that means this is present in the tissue. This state is present in the tissue in our body, and this R state which is present in the lung. What happened here? This T state which has a low affinity to bind the oxygen, and here this T state which get converted to the R state where this has the high affinity to bind the oxygen. Okay, that means what happened here? The binding of oxygen to the hemoglobin is cooperative manner. Okay, the presence of the bound oxygen favor the addition of more oxygen. The hemoglobin molecule goes from tense. Here this hemoglobin molecule always goes from tense to relaxed state. This cannot be convert relaxed to tense. This always convert from tense to relaxed state. Tense state that is stands for T, and relaxed that is R, that means relaxed state. Here why? Because this T state is called as a deoxyhemoglobin, and R stands for what? Oxyhemoglobin. Okay, and that's why here T get converted to the R state. The pocket of the hemoglobin get more easy for the following oxygen unit to access due to the breaking of some weak interaction. This happened like a chain and the pulley. The pulling of this proximal histidine along with the activity of the Fe getting into the plane of the porphyrin this triggers this activity. What happened here? In the T state, this Fe which is present above the plane of the porphyrin ring. Okay, and whenever the oxygen is bind to the Fe, this Fe get convert to the or get push into the porphyrin ring and get converted to the planar state. And here that planar state has the high ability to bind the oxygen. Here you can see the structure of the T state. This is the hemoglobin unit. Okay, and here this is a T like structure. Okay, this is the this structure is what? Very tense. Okay, and this structure, what happened here? Sorry, in this structure, this is a deoxy form of the hemoglobin. This structure is called as what? This is the deoxy form of hemoglobin. This structure, this R structure is, or R state is called as what? Oxy form of the hemoglobin. Okay, here what happened? The dimer of the hemoglobin which is ionic, and the hydrogen bond which prevent the movement of the polypeptide chain in case of T structure. But in case of R structure, what happened here? It rupture, it break down the ionic and the hydrogen bond between the dimer due to a bonding of the oxygen. So the polypeptide chain have the more freedom to move. Okay, that's why this is called as a relaxed structure. Do you understand? The hemoglobin has a two state, tense, that is a T, and relaxed state. This tense is called as a deoxy state, and relaxed state is also called as oxy state. This shows the cooperative effect. Okay, what is the question asked in the examination related to this topic? Here the T state of the hemoglobin shows oxyhemoglobin, deoxyhemoglobin, none of these. This shows what? Deoxy form or deoxy state. Okay, and the relaxed state shows the oxyhemoglobin state. Okay, next topic, that is what? The hemoglobin shows an allosteric protein. This is an what? Allosteric protein. What is the allosteric protein? This allosteric protein does not have the fixed property. Okay, its functional characteristic are regulated by the specific molecule present in its environment. That means what? Allosteric protein, that means as we changes the environment, they changes their character. That is called as what? The allosteric nature of the protein. Okay, then the function of hemoglobin in the living system is regulated by the oxygen partial pressure. Okay, the hemoglobin function, which is regulated by what? The partial pressure, second H plus concentration, and third, that is 2,3 diphosphoglycerate presence. Okay, let me see here the allosteric structure and the Bohr effect. First of all, let me see the allosteric nature. Here this is the graph of saturation with the oxygen versus pressure, partial pressure of the oxygen. Okay, here as the pressure is decreases, as the pressure is increases, their oxygen level also increases, and as the pressure, partial pressure of oxygen is decreases, then what happen? The affinity to bind the oxygen to the Fe or the hemoglobin is going to decrease. That means what? At this position there is a low partial pressure of the oxygen. That means this, at this position, hemoglobin, which is present in what? Tissue. This is present in tissue. And here from left to sorry, right, here this, there is an increasing partial pressure of the oxygen, and that's why here at this position the hemoglobin, which is present in the lung, because at the lung position, where the oxygen hemoglobin bind the oxygen, and then after binding the oxygen, it transport this oxygen to all over our body or tissues. Okay, here let me see the allosteric nature. The myoglobin, hemoglobin shows the allosteric protein, but myoglobin is not. That means myoglobin does not changes their property, their characteristic by changing the physical property. That means by changing the pH, by changing the pressure of the oxygen, the myoglobin does not change their graph or the properties. But hemoglobin, which shows changing their specific characteristic by changing the environment. Okay, that is called as a allosteric protein. What happened here? This, in case of myoglobin, when we plot a graph, the saturation with the oxygen versus the partial pressure of the oxygen, this myoglobin shows the hyperbolic curve. Okay, they shows the hyperbolic. That means at this position there is a suddenly increase in the it increases suddenly, and what happened at the saturation point? Here at this point they shows the linear nature. That means they shows the hyperbolic nature of the graph. But in case of hemoglobin, what happened? First of all, slowly changes in the partial pressure, and then suddenly increases the partial pressure. That means at this position there is an increase in what? The affinity of the binding of the oxygen, and then at the saturation point it shows the linear structure, linear nature. Okay, and that curve is called as a sigmoidal curve. That is called as what? Sigmoidal curve. Okay, remember that always asked in the examination. The myoglobin shows in a allosteric protein, myoglobin shows hyperbolic curve, and hemoglobin always shows what? Sigmoidal curve. Okay, then next, this sigmoidal curve is changes by changing the pH level. First, this curve changes by what? Changing the partial pressure. As the partial pressure is increases, the affinity to bind the hemoglobin is increases. As the partial pressure decreases, affinity to bind the oxygen to the hemoglobin is decreases. Second factor, pH. Okay, what happened here? As the pH 7.6, at this position what happened? There is a suddenly increase in the pressure, and then at the saturation point, when this one means what? Here at this position there is a high ability to provide the oxygen, and then it goes to the saturation point, linear. Okay, then what happened here? As the pH is decreases, the affinity to bind the oxygen to the hemoglobin is going to decreases here. Okay, that effect, and the ability or affinity to bind the H plus ion in the hemoglobin is going to increases. That is called as a Bohr effect. Let me see in detail what is the Bohr effect. Here, this Christian Bohr, it is a father of Niels Bohr, discovered this effect. That's why it is called as a Bohr effect. An increase in concentration of the proton or the carbon dioxide will reduces what? The oxygen affinity of the hemoglobin. Here what happened? The chemical basis of the Bohr effect is due to the formation of salt bridge. That means as the pH is decreases, then affinity to bind the oxygen to the hemoglobin is going to decreases, and affinity to bind the carbon dioxide is going to increase. Why this happen? Because whenever the pH is going to decreases, there is a formation of the salt bridge of the quaternary structure. How this form the salt bridge? One of the salt bridge is formed by the interaction between histidine and the lysine. Okay, that means how the salt bridge is formed? This can be formed by the interaction between these two amino acids, that is histidine and the lysine. This connection will help to orient the histidine residue to also interact in another salt bridge formation with a negatively charged aspartate. The second bridge is formed with the aid of an additional proton on the histidine residue. Below the pH of 6, the imidazole ring of the histidine is mostly protonated, and that's why it's favoring the salt bridge formation. That's why here, after the formation of the salt bridge, the affinity to bind the oxygen is going to decreases. This is about the the Bohr effect, and what? Allosteric protein, and the sigmoidal nature of the hemoglobin. You can see here, this is the nature of the myoglobin. This is the parabolic nature. In second case, this is the hemoglobin nature. This is the HbF, that is a fatal hemoglobin nature. This is the fatal hemoglobin nature. At this fatal hemoglobin nature, they have the low pressure, and at the that means it has a low affinity to bind the oxygen, and in the in green color line, that is the hemoglobin A type of the hemoglobin, which is present in the adult. This type of hemoglobin present in adult, and here HbF, this type of hemoglobin which is present in the fetal. Okay, here saturation of the oxygen on the hemoglobin F, that is called as a 23 BPG. Okay, this BPG we will learn next time. What is the BPG? What is the fatal HbF? What is the HbA and the HbS? Mostly the hemoglobin has a three types: hemoglobin A, hemoglobin F, and the hemoglobin S. All these type of the hemoglobin we will learn in the next lecture. Today's lecture we learn about the mechanism of the hemoglobin. The deoxyhemoglobin and the myoglobin and the hemoglobin show the same type of the mechanism of the binding of the oxygen. What is the difference of that? Only one difference is there. The hemoglobin, which has four quaternary proteins, and that's why in the quaternary protein there are the four hemoglobin which binds the four oxygen molecules, and in case of myoglobin there are only one protein molecule, and that's why only one heme group is bind to the oxygen molecule. What happened? First of all, in the deoxy form, this is the high spin form of the Fe having +2 oxidation state, and this Fe which is present above the plane of the porphyrin ring. This is very important. And whenever this histidine which is present in the proximal state, and then whenever the oxygen is bind to the how this oxygen bind to the Fe, this proximal state of histidine is get converted to the distal stage, and at this position the histidine which pull this Fe inside the porphyrin ring, and this Fe which is put inside the porphyrin ring and form the planar structure. And then after formation of the planar structure of the Fe, then this oxygen molecule which binds in a bended shape, and that's why here this has more affinity to bind the oxygen to the Fe. If this Fe which is not present to the planar shape, then the Fe has the ability to bind what? The more and more CO, because CO which has the affinity to bind the linear manner to the Fe, and for avoiding this proximal histidine get converted to the distal histidine. Okay, next we will learn that is what are two state of hemoglobin, that is the T and the R state of the hemoglobin. T state is called as deoxy form of hemoglobin. R state is known as a relaxed form of the hemoglobin. Always T get converted to the R state. Next we learn that is what allosteric effect and the Bohr effect. Okay, here this hemoglobin does not show the allosteric protein, that's why here there not be changes, and they shows the hyperbolic curve, and the hemoglobin shows the allosteric protein, that's why they show the sigmoidal curve here. And the pH of the hemoglobin decreases, the affinity of the hemoglobin to bind the oxygen is going to decreases. Okay, this is about what today's pattern, that is what the mechanism of the hemoglobin and some factor affecting on the hemoglobin. Okay, thus thank you very much for watching this lecture. Next time we will learn the different types of the hemoglobins. Okay, comment on the each videos. This is attendance for you. Thank you very much.